Welcome to this lecture on strong induction. But before we start this new topic, let's review good old mathematical induction. Now remember that we used it to prove theorems of this form. For all n in Z plus, P of n is true. Now in some theorems, n does not range over the whole set Z plus. Instead, n is greater than or equal to some integer constant a. So can we modify mathematical induction to handle this kind of theorems? Well, the answer is yes. We can just modify slightly the inference rule. For example, we can change the first premise to P of a instead of P of 1. And then in the second premise, P of k implies P of k plus 1 must be true when k is an arbitrary integer greater than or equal to a. If these two premises are true, then we can infer that for all n greater than or equal to a, P of n is true. And that is a more general version of the inference rule for mathematical induction. Now, why does this rule make sense? Well, again, if P of a is true, and P of a implies P of a plus 1, then we can infer P of a plus 1. If P of a plus 1 is true, and P of a plus 1 implies P of a plus 2, then we can infer P of a plus 2, and so on and so forth for all values of n greater than or equal to a. So as before, for every proof by induction on n, we're going to have to write two subproofs. The first one is the basis step, where we prove that P of a is true, and the second subproof is the inductive step, when we prove that P of k implies P of k plus 1 for an arbitrary integer k greater than or equal to a. And as usual, the inductive hypothesis is going to be the hypothesis of the conditional here, namely P of k. Now, let me tell you a quick story. When I was young, that was back in the previous century, people used to write letters by hand and stuff them in envelopes, and then apply postage to the envelope, and then send that through the mail. Now, it turns out one day I inherited several boxes of stamps, and these boxes only contained two kinds of stamps, 3-cent stamps and 5-cent stamps. So I was thinking, well, what can I do with those stamps? Clearly, any postage equal to 8 cents I could take care of by adding a 5-cent stamp and a 3-cent stamp. But how about if my postage was 9 cents or 10 cents or 11 cents, on and on? How many of these amounts of postage, called n, could I actually form using only 3-cent stamps and 5-cent stamps? Well, I sat down right away and I tried to prove a theorem. And here is the theorem I managed to prove, is that a postage amount of n cents can always be formed using only 3 cents and 5-cent stamps, as long as the integer n, the amount of postage, is larger than or equal to 8. Now you guessed it, the way I proved this theorem was by using mathematical induction. But notice in this case I couldn't start at 1, I had to start at 8. So let's go ahead and prove this theorem, which I copied on the top of this new slide. So as promised, we're going to do a proof by mathematical induction on n. The first step is the basis step, where we're going to prove P of 8. So P of 8 states that postage of 8 cents can be formed using only 3-cent and 5-cent stamps. Well, that's definitely true, since all we need to do is take one stamp of each type, since 3 plus 5 is equal to 8. And that completes the proof of the basis step. Now let's write the proof for the inductive step. We start by assuming that P of n is true as long as n is an arbitrary integer greater than or equal to 8. So we can use the inductive hypothesis right away, that is P of n, to infer that postage of n cents can be formed using only 3-cent stamps and 5-cent stamps, let's just give a name to this number of stamps. So X is the number of 3-cent stamps and Y is the number of 5-cent stamps. So in other words, the number of 3-cent stamps times 3 cents plus the number of 5-cent stamps times 5 cents must be equal to the postage N. That's the inductive hypothesis. Now, what we must prove is that it's possible to form a postage of N plus 1 cents using only those two kinds of stamps. So let's divide our proof into two cases. The first case is that Y is equal to 0. In other words, we only use 3-cent stamps to form the postage N. Well, since N is greater than or equal to 8 and we only used 3-cent stamps, we must have used at least 3 of these stamps. So let's replace the 3 of these X stamps by 2 5-cent stamps. So what happens? Well, you have 3 times 3, 9 cents, which we replace by 2 times 10, 2 times 5 equals 10 cents. In other words, we just added 1 to the total postage. So let's write this down. We started with 3x, which was equal to n. We subtracted or took away 3 3-cent stamps, so minus 9, and then we added 2 5-cent stamps. So what do we get? Well, we get 3x minus 9 plus 10, that's 3x plus 1. Hey, that's n plus 1. So what we just proved is that in the case where we don't use any 5-cent stamp to form the postage of n, it is possible to form postage of n plus 1 cents using only 3-cent stamps and 5-cent stamps. In particular, we used x minus 3 3-cent stamps and exactly 2 5-cent stamps. And that's the end of the proof for the first case. Now let me emphasize that this replacement here can only happen when we have at least 3 stamps of that kind. And this was only guaranteed when y equals 0. That is, we didn't use any 5-cent stamp to form the amount n. So what happens when we actually use at least 1 5-cent stamp to form the amount n? Well, that's case number 2. Y is greater than or equal to 1. Now, we won't be able to follow the same reasoning as in case 1, but here is what we can do instead. Since we used at least 1 5-cent stamp to form the amount n, then we can pick one of those 5-cent stamps and replace it with 2 3-cent stamps. So what does that mean? Starting from an amount of n cents, we subtract 5, and then we add 2 times 3 equals 6. We obtain n plus 1 cents. And to do that, we only use 3-cent and 5-cent stamps. So in conclusion, the postage amount of n plus 1 cents can be formed using exactly y minus 1 5-cent stamps and x plus 2 3-cent stamps. So we were able to prove that P of n plus 1 then holds for both case 1 and case 2. And this concludes the proof of the inductive step. Now together, the basis step and the inductive step prove theorem 1.